think Bruce.
Hello, John.
Hey, Bruce.
Hey, that looks like your wife.
It is.
Linda?
In a separate room.
In a separate room? You guys doing some social distancing?
No. Well, your wife's in a separate room.
That's an interesting, looks like a ceramic deer. Doesn't look like a veterinarian's
It's ceramic. It's not an actual deer.
Yeah.
It's ironic.
Okay, that's true. That's fair. But it is a head, just a head. I'm reading something called The Devil in the White City. Have you ever heard that story?
I've read that book.
The Chicago World's Fair.
Yeah, I've heard, yeah.
So it jumps back and forth between the Chicago World's Fair and this pharmacist who incinerated women as a hobby during the World's Fair. It's it's awful.
It's one of the few books that I read years ago and still haunts me.
Yeah.
It's true because it's a true
We
story.
own that book, John. You could read it.
I assume he was the devil, the man who
It's
incinerated
true.
people.
It is true.
So so what I'll do, John, is I'll do a little introduction, and I'll talk about, you went to Caltech and Georgia Tech, worked Xerox, FLIR, and Lam Research.
It's technically Tektronix before it became Xerox.
Okay.
And my PhD is actually from the University of Arizona.
Oh, is that right?
Yeah.
Yeah, that's true. Yeah.
I did some postdoctoral work at Georgia Tech.
Right. At least that was smart to go to Arizona, get some nice weather.
Exactly.
So we sent this out fairly broadly. I've got a friend on the East Coast that worked at EMC, so this is interesting to him.
Oh yeah.
And another guy back there says he might want to do a talk on a similar subject.
Cool.
Said he could do some studying on it. But I don't know. I sent it to Alan Douglas, and I don't know if he's going to do it. I'm going to try to record it.
Yeah.
Allegedly, it's going to be recorded because that's what I put down for.
Hey, it says it's recording all of this.
Yeah. And I don't think I have to do anything special. I made it so that participants could share their screen, which means, and the only one that can kick you off is me.
Okay.
So, and there's Greg Gatta. Hi, Greg.
Hey, Bruce, how you doing?
Good. So what you see right now, you'll see Melinda, who is John Wiltse's wife, with the ceramic deer behind her. And then we have John Miller, who did the extraterrestrials presentation last week, who I'm sure we'll hear from again. Greg used to work at, you worked for various companies, right? Started with Aetna.
Yeah, I started in the insurance. I was in a software engineer pretty much my whole life, but I started at the Aetna, and then we did couple of software startups, I was at Symantec for about 10 years, so really focused on internet security, and then finished my career at EMC, so.
Okay, you're the EMC guy.
Yeah.
Okay.
So all of a sudden, what I found on these meetings is everybody comes in, usually people come in early, but most people come in up to 5 minutes late, so we'll see how that goes.
Let's see.
Yeah.
Hi, Joe. Is that John Miller?
There's Vicky. Hi, Vicky.
Oh.
We have a few of us nerds here of various sorts. Not you, Vicky, but.
No.
So the guy up in the corner there, youngish looking compared to me, is John Wiltse, who's going to be doing our presentation tonight on 3D NANDs. And then we have Greg Gatta, who I went to high school with ages ago, who became an executive in the software industry. And over here is Randy Whiteside. He and I once saved FLIR systems by, by working 60, 70-hour weeks, right?
Nice.
Yeah. Yeah. Oh, and Scott Corbett,
Hey, Bruce.
who was a sound engineer and also a musician. Yeah.
Yeah,
Hi,
in
Scott.
part.
It looks like we have Brett Madsen, who may not quite have this, IT stuff figured out yet.
Well, he'll get it. There's David Dunning. He and I sing in the choir together, and David is a PhD educator.
Nice.
Yeah. Randy, are you still working, or have you retired, or?
Yeah, retired now.
Okay. Scott is still working, I know. John is still working, Melinda is. And who is next?
No, I'm not working. I'm like Randy. I am semi-retired. I love it.
Yeah, it's great.
Cool. Then we have Edward Friedman. Hello, Edward.
Yeah. Do I have, can you guys hear me?
Yep.
Yeah.
Yeah, okay, so I have to excuse myself right now because I apologize. I am a friend of John Miller, and I know that'll be a shock.
And you have to apologize for that, Ed.
That's
Yeah,
a confession of a sort.
That's, just want to warn you ahead of time. If you want to mute me, you can.
No, we invite all comers. In spite of their,
So Ed, I've known Ed for like 35 years, and he has to apologize for being my friend. Thank you, Ed. I have to.
we can make that a blanket apology.
A blanket apology on me. You're welcome.
So let's wait just a couple more minutes and see what else we get here.
FLIR person.
I know Brett is working on it, working at getting on here. He told me this is his first Zoom meeting.
So for those of you not familiar with the joke, Brett was like our IT guy for years and years at FLIR. So
yeah, it's kind of strange that he's having trouble, but he may have a problem because he's in Florence, and it may be a problem with his connection.
yeah.
Oh, nice.
He went from IT, and now his hobby now is riding bicycles on dunes down by the coast.
Yeah, it looks like that's part of his online name.
Yeah. And this next person you see here is Noel Jolivet.
Oh.
Oh, Joel.
Noel has the distinction of running a project for what, 6 or 7 years, and he gets the Stamina Award.
Yeah, and I've seen his ass like 3 times. He's mooned me totally 3 times. I should have fired him years ago.
That's your only claim to fame, isn't it, John?
He's not unique in that respect. So I think what I'll do is, let's see, what do we have here? It is now 34. At 6:35, I'm going to introduce John. We'll get started, and other people will straggle in.
By the way, hey, Randy, good to see you.
Yeah, good to see you.
Well, at least we don't see your ass, Noel.
John has some sort of hang up about that, doesn't he?
I noticed that. I wonder what that's all about. Okay, so here we go. John Wiltse is a product of Caltech, where he got his bachelor's degree. University of Arizona, where he got a PhD in mechanical engineering, I think specializing in fluids. And then Georgia Tech, where he did postdoc work, until one day he woke up and said, hey, I ought to get a job. He went to Xerox, actually Tektronix, which eventually turned into Xerox, working on inkjet stuff. And then, was it started FLIR in the 1990s? It was there until 2011 or something? Maybe 2013?
2015.
Okay.
5 years.
And then now he's at Lam Research and seems to have found a home there. And I think I will say that he's one of the best engineers I've ever worked with. And I look forward to his presentation.
All right.
John Miller?
And me too. And me too. Unlike Noel. Me
Yeah.
too.
Okay. So if everybody can mute yourselves there, we'll listen to John's presentation. John,
Right.
take it away.
All right, let's see if this works. Do-do-do. All right. Can everyone see my PowerPoint? Nod your heads if you can see it. Everything good? Good.
Yep.
All right. So today I'm going to talk about a subject called 3D NAND. I'll define that a little bit later in my talk. But I'll talk about 3D NAND and how it's disrupting the computer storage industry. First, I'm going to start with a personal anecdote. So my first computer, which I bought in the early 90s, had a 40 megabyte hard drive. That's megabyte with an M. I was a poor graduate student at the time. I could not afford the optional huge 80 megabyte hard drive that this computer also came with. So flash forward about 30 years, and the other day I was rummaging around in my junk drawer, and I found this thing in my junk drawer. And it's a micro SD card. It holds 128 gigabytes, so that's 3,200 times the storage of my Mac 2SI. And if you want to buy it, this particular brand sells for $15.99 on Amazon. So how do we get from an almost unaffordable 40 megabytes to just a commodity 128 gigabytes? Well, so persistent data storage, which includes hard disk drives, has evolved through the process of disruptive innovation. That's a term coined by Clayton Christensen in a 1997 book. And what has happened is, if you look at the capability of hard disk drives from the period of about 1975 through 1995, the storage space in megabits per square inch has increased exponentially. And leading firms have had an outstanding record of technological innovation, where they've just followed that exponential curve. Then occasionally there were technology leaps where they went from, for example, ferrite oxide heads to thin film heads to magneto-restrictive heads, and it would move up a little bit higher along that curve. They're basically able to give their existing customers more and more of what they want very, very efficiently in terms of megabits per square inches or megabits per dollar. But the interesting thing is, all of these companies ended up losing market share, and most of cases even going out of business due to less capable competitors. Why did this happen? Well, something called disruptive innovation occurs when niche applications become good enough for the mainstream. So back in the early or the mid-1970s, most hard disk drives were 14-inch drives because the main market for them was in the mainframe computer market. And again, if you look at the curve, the capability of this in terms of megabytes increased basically exponentially over time. But an interesting thing happened. Another market came up, the mini computer market. Now this drive was much smaller than the mainframe market at the time, but because the computers were smaller, they couldn't no longer, you couldn't put a 14-inch hard drive in it. So they had to be smaller, in this case 8 inches. But what happened is that as the capability of this 8-inch drive increased, it got to the point where it actually moved faster than the demand in the mainframe market, and 8-inch drives overtook and became the nominal hard drive in the mainframe market as well. A few years later, the same thing happened with 5¼ drives, which were first developed for use in the desktop PC market. They became good enough to overtake 8-inch drives in the mini computer market. And the cycle repeated over and over again. Now note that these drives were not better, at least in terms of megabits per square inches or megabits per dollar, compared to the drives they were replacing, but they were good enough to steal market share and in most cases put the other companies out of business. So what we see is that over time, hard disk drives became smaller and simpler. The very first hard disk drive was invented by IBM in 1956. It consisted of 2-foot diameter disks, 120 of them stacked together, and it stored all of 5 megabits. In the early 90s, Maxtor and other companies had kind of a typical 5.25-inch drives, which held on the order of 110 megabytes or something on that order. Then finally you go today, you can buy one of these Toshiba drives. It's a 3.5-inch drive, much, much smaller, much, much simpler. It holds 5 terabytes of data. So in other words, that's 5 million megabytes of data. It would take 5 million of these things, 1 million of these to hold the same amount of data as one of these modern Toshiba drives. And this is all in the span of one human lifetime. But now what we're starting to see is that mechanical hard drives are also being displaced by solid-state hard drives, SSDs, also known as flash drives, that use something called 3D NAND. Like some of these smaller hard drives that ended up being disruptive technologies, flash storage was originally in a niche application. For example, camera memory cards, smartphones, tablets, things of that nature. But as time has come along, they've started to move into solid-state hard drives, which can actually plug into and replace, the mechanical spinning hard drives that are currently used in computers. And if you look at the trend over the last 10 years or so, and actually project it out into the next couple of years, what you see is that the number of mechanical hard disk drive shipments is going down year over year, whereas the number of solid-state hard drive shipments is going up and up over time. And finally, it's projected that roughly next year, the number of solid-state drives is actually going to pass the number of hard disk drives in terms of the number of total numbers of units shipped. Another thing I'd like to point out is if you look back in about the year 2012 was when Samsung first introduced something called 3D NAND. And that was really kind of the catalyst of this growth. And we'll talk about that in a little bit more detail later on. All right, so the remainder of my talk is going to be sort of an inside-out view of how 3D NAND works. We'll start out with an individual storage element, how those are combined into what's called a NAND array, then how that NAND array is in turn packaged into a 3D NAND flash memory, and then finally we'll get into a little bit about the fabrication techniques. Now, I realize that I have not actually defined properly what 3D NAND is. I have not defined my acronym, even though I've repeated it over and over and over again. So I apologize for that. But it really isn't all, well, it is important. I'll get to what it means. But let's just say that NAND stands for not and it basically just refers to the way the individual memory cells or the storage elements are connected in these memory arrays. Okay, so to know how a storage element works, you first need to know, at least at a cursory level, how a field effect transistor, or FET, works as a switch. A transistor basically consists of a hunk of silicon. It has a couple of elements, doped silicon called source and a drain. And then on top of that, it has a gate oxide, which is essentially a glass. It's a non-conductive material. And then on top of that, it has something called a control gate, which is a metal, copper or tungsten or something like that. And it basically functions as a switch. It has one of the key attributes of it is there's something called a threshold voltage. And when you apply a voltage to this control gate that is above the threshold voltage, it creates something called an inversion layer. Here, this little trapezoidal thing that allows for current flow between the source and the drain. So ID stands for current, VGS stands for the gate voltage, VT stands for the threshold voltage. So again, just to kind of sum up this slide, off, meaning no voltage applied to the control gate, current can't flow. It basically acts as if a switch is off. When you apply a large enough gate voltage to this device, it acts as a switch that's on, and current can flow through the body of the transistor and then out. Okay, so that's great. That's your switch, but how does it act as a storage device? So a 3D NAND storage element, or a charge trap device, adds a storage element, also known as the trap, to this FET. And the two additional layers you're adding are something called a charge trap layer and the tunnel oxide. So the tunnel oxide is just another oxide layer, exactly like the gate oxide. The charge trap layer is new. It can be made of various different materials. And it has the ability to basically store electrons in it for a long period of time. One of the major flash memory makers described the charge trap layer as being like cheese. That is not my analogy. I'm not totally sure how this is like cheese. I would call it a sponge, but he said it was like cheese. But it holds electrons so they can't escape. So once you get electrons in there, then they're there essentially forever. This has an interesting effect on the threshold voltage. Remember, the threshold voltage is a voltage above which this switch basically turns on. So when the storage element is erased, the charge trap layer is empty, and you have just sort of the normal low threshold voltage that you would have in a transistor. When you program it, meaning you put a bunch of electrons in this charge trap layer, it raises up the threshold voltage, and thus it takes more voltage to be applied to the gate to turn this switch on. So then you can use this to tell whether or not it's programmed. So to read a charge trap device, you need to apply voltage somewhere between the off threshold voltage and the on threshold voltage. And so here I'm sort of using a couple of different voltages for illustration purposes. But if we assume that the threshold voltage of an erased charge trap device is something on the order of 3 volts, and then you apply 4 volts to the gate, you will see current will flow because you're above this threshold voltage. On the other hand, if this charge trap device is programmed, the threshold voltage is raised. So let's say it's 5 volts, for example. Now if you apply 4 volts to the gate, no current flows. So basically you can tell whether or not your charge trap device is programmed or not by applying a voltage of 4 volts, say, and seeing whether or not you have current. Okay, so how do you program these things? It's a little more complicated. I'm not going to go into a whole lot of detail, but essentially what you do is to program these things, if you apply high enough voltage to the gate and to also to the drain, it ends up pulling electrons up from the drain into the charge trap layer. They get trapped. To erase it, you do the reverse. You put in a high enough negative voltage to this, and that ends up pushing all the electrons out of the charge trap layer back into the drain where they go away. So you can both program and erase these charge trap devices. Okay, here's where I actually tell you what NAND is. Okay, a NAND array combines several storage elements so that they can be easily read without having an individual wire to each one of the elements. So here I show sort of a cartoon or a physical representation of 8 charge trap devices in an AND array. And here's the electrical symbols of that same thing. And the way you would read this, read any given element of this, would be you would apply a high gate voltage to all of these elements except the one you really want to investigate. So in this case, again, if we're saying that the threshold voltage of an erased device is 3 volts and the threshold voltage of a programmed device is 5 volts, if you apply a voltage of 6 volts to all of these elements, then clearly you're above the threshold voltage and current can flow through this whole array. It can go through here, boom, boom, up, down, all the way through this device and out. But if you want to find out if this particular element is programmed or erased, you apply a voltage somewhere between the erased threshold voltage and the programmed threshold voltage. Again, for illustration, I again assume it's 4 volts. Now, in this case, if this element is programmed, then it will not conduct. If it conducts, then that means that this element is erased. So if it's erased, this device's threshold voltage is 3 volts. You apply 4 volts to it, it conducts. If it happens to be programmed, its threshold voltage is 5 volts, and it would not conduct. And that way, you can one by one read all the elements in this string. Okay, now my real talk is about 3D NAND. So how do we get from 2D NAND to 3D NAND? So in 2D NAND, the storage element we're talking about is planar. As you can see here, it's the same thing we've been talking about where you've got the silicon body, source and drain, a couple of oxides, a charge trap layer, control gate. The clever thing about 3D NAND is that this is all made cylindrical. And by the way, this is all done in a part of the device called a channel hole, but we'll get to that later. So this silicon body just becomes a big long rod. Around that, you have a charge trap layer, and around that, you have this metal control gate. And between these, you have small layers of oxide as well, just to keep current from flowing inadvertently from one to the other. Okay, well that was how you do a storage element. How do you do an array? Well, you can basically fold up a 2D NAND array vertically and turn it into a 3D NAND array. And so on the left, again, we've got the 2D NAND array with all the different storage elements. And these are all basically folded over into this 3D NAND array. So in both cases, as I show here, we have 8 storage elements or charge trap devices. In the 2D, they're all laid out in a line, but in this 3D NAND, they are kind of in this U-shaped channel. So you've got 1, 2, 3, 4, 5, 6, 7, 8, and then another set over here. The base silicon is now all in a big long cylinder, and again, this is in something called the channel hole. Around that, you have this sort of magenta purple element, which is the charge trap layer. And then these green elements are called the control gates for this. The bit line, again, is mapped like this, and there's something called the source line as well. So basically everything kind of maps one-to-one as you go from the 2D NAND to 3D NAND. All right, 3D NAND fabrication is a multi-step process that includes several different deposition and etch steps. I'm going to show this little video. It's available on YouTube if you want to watch it later, but I think it's a good illustration of the different steps.
To address the demand for more storage capacity, 3D NAND structures build vertical strings of memory cells. Let's take a look at some critical steps in how 3D NAND is made. The manufacturing process starts by depositing thin alternating layers of materials, such as oxide and nitride films.
So that's called the mold stack.
Highly uniform and extremely smooth. To define the vertical channels, a hard mask is deposited and openings are formed, followed by high aspect ratio etch through all the layers, which define the size and shape of the memory channel holes. Contact pads to the word lines are created using controlled etches that produce the distinctive staircase-shaped structure. To form the slits, a hard mask layer is deposited, and openings are patterned. Slits are then etched to separate the columns of channel holes from each other, creating an array of memory cells. In some 3D NAND schemes, the nitride layers are removed and tungsten word lines are then created, with an inside-out atomic layer deposition process. By stacking cells vertically, 3D NAND offers higher bit density for increased memory demand. Lam's advanced deposition and etch systems are making high-volume production of 3D NAND devices a reality.
Hey, John, I have to leave, believe it or not. I have a 7 o'clock Zoom meeting that I already had signed up for, so.
Oh, all right.
Sorry. See you guys later.
Okay, bye, Noel.
Bye.
All right, moving on. All right, so.
He's a party pooper.
Yeah, what the heck? All right. So the first step in that process was called the mold stack, and that was the alternating layers of silicon oxide and silicon nitride. The mold stack is deposited using a process called plasma enhanced chemical vapor deposition, or PECVD. And so this is actually this is the kind of product I work on now. So this is kind of my little niche in this process. Here I show a really simplified view of how these reactors work. There is a pedestal that both holds and heats the wafer. It needs to be heated up to a relatively high temperature to do this. And then on the other side of that, there's something that's called a shower head. It literally is called a shower head simply because it looks exactly like a shower head. And this is a gas delivery system. The gas flows in through the top and then out a bunch of small holes in the bottom of the shower head. But these two elements also act as electrodes. And typically what you'll see is that the pedestal will be grounded and the shower head will have an RF generator connected to it, radio frequency generator. And that will put a high voltage, high frequency power into the shower head, which will create a capacitively coupled plasma between the shower head and the pedestal. And then this plasma is what helps to react the different reactants and create the two films that we see in the mold stack. So plasma provides the activation energy to allow these reactions to occur at a lower temperature than they would if there were no plasma, if it were just a thermal reaction. And so if you look at this cute little animation here, what we have is as the plasma is causing these reactions to occur, the mold stack is being built up. Silicon oxide is typically done with a chemical called silane. It's a very common one. It consists of silicon and hydrogen. You just add oxygen to that and put it in a plasma, and it turns into silicon oxide, which ends up on the wafer. Very similarly, silicon nitride is done with silane as well, except in this you react it with ammonia. Again, it tends to split it up. You get silicon nitride and some byproducts. And so just by putting down alternating layers of this, you can build up the mold stack, which is the first layer in making 3D NAND. Here I show 4 pairs of oxide and nitride, where modern 3D NAND has quite a bit more layers than that, but this is a good illustration of what's going on. All right, that's pretty much all I have, but 2 things I'd like you to take away from this talk. First thing is that 3D NAND is the next disruptive innovation in persistent data storage, as you can see from the plot below, where solid state hard drives are beginning to overtake and pass mechanical hard drives. And then number 2, even if you don't remember all the details, try to remember some of the clever techniques that 3D NAND uses to arrange some of the storage elements vertically to maximize density on the wafer. All right. What questions can I answer for you?
So this is Greg. If I, my background at EMC, again, it was incredible. I mean, when I got there in 2012-ish, everything was spinning drives.
Yep.
I mean, the buckets of earplugs when you went into the data center, I mean, you're talking about building, terabyte storage arrays, and you saw a lot of the flash players showing up in the marketplace, and I think as you described, they were more niche. They were going after very specific applications and the like. And then suddenly, it just exploded, such that again, EMC actually had to go out and do an acquisition because they were so behind the curve and the like. And then, as things would have it, again, because these were kind of niche players, the salespeople went out there and sold it for everything under the sun. There were certain things that it just, couldn't stand up, to. The good news was that the VMAX architecture, which was the original big, heavy duty, EMC storage array, was architected and had already been, you could spec, it was a hybrid array. So you could spec flash into the array, but you were lucky to get like 5%. And then overnight, I mean, it went 40, 50, 60, and, such that now I'm not even sure they ship spinning drives anymore.
Yeah.
I mean, the software that was required to manage spinning drives behind the scenes was incredible.
Right.
I mean, the RAID configurations you'd have to put this stuff into, depending again upon the application and how much redundancy you wanted, was incredible. They had a huge problem where the disk drive makers were having, and had some failures out there, such that they had to put even more software into the drives just to figure out and start telling us, when were these hard drives failing.
Mm-hmm.
When I was there for about 4 years or so, I don't think we had a single flash failure.
Yeah. No, they're very robust. They're lower power. They're
right.
A lot of advantages. More expensive in terms of like dollars per megabyte, but
right. But coming down at a rate and pace, and when you just started adding it up, power, footprint, battery backup, all that kind of stuff. I mean, it was wiping out spinning drives at a rate and pace that I hadn't really seen. One question that I had is that I believe that you can read this stuff forever, but when it comes to write, these things do have a life expectancy to them. What drives that life expectancy? Because I do think there's a quality thing out there too, in terms of when you're buying this stuff, there's different grades.
Yeah. Honestly, I do not know.
Okay.
It's a simple answer.
Yeah, fair enough.
Yeah.
But yeah, there was, and nobody thought that this stuff was going to wear out anytime soon, so to speak. But you did have to kind of sort of look at your application and decide, was it write intensive and that type of thing. And then, you'd have to do things to move the writes around in the box, so that you weren't just like beating the crap out of one segment of the array.
Yep. The one thing that's happened to make them more reliable is the charge trap layer is now an insulator.
Mm-hmm.
There used to be something called a floating gate, and that was a lot less robust. So that whole charge trap layer that's like a piece of cheese that holds the electrons made it a lot more robust than the previous generations.
Right. Cool.
Yep.
Yeah.
Hi,
no.
John. This is Katie. Oh, sorry.
Hey, Katie.
Hello. Thank you very much for the talk. It was very cool and very informative. So beyond the two things that you'd like us to take away from this talk, what do you think is going to be the next exciting thing? Where do you think it's going from here? Yeah, you knew I was going to ask that.
Yeah. So one thing I think that is a really interesting field is quantum storage. At this point, I don't believe that that's persistent, meaning I don't believe there's a way to store information after power is removed. But I think that really, I mean, there are so many people working on quantum computing now. I think that that's, and quantum storage.
Yeah,
that,
being able to tie all these things together.
Yep, I think that'll be the next big thing.
Cool. Okay. Yeah, it'll be interesting to see how, you know, we've gone from planar to 3D. So now if we can go to 3D to networked, that could be cool.
Exactly. Yeah.
John, this is Scott. I'm wondering what the fab facilities look like for this and how they are different than, say, conventional semiconductor, particularly the deep aspect ratio etching and so on. I'm just wondering what the details of the fab look like and what the typical resolution size is. You know, they talk about semiconductor
Yep.
dimensions that
Yep.
entail with the photolithography and so on.
Yep. Well, a couple things. I mean, first of all, that's really the main reason that 3D NAND was developed, was to get away from having to go to smaller and smaller features to allow you to store more data in 2D NAND. So instead of getting smaller and smaller, it just started building up and up and up. In terms of the equipment, the type of equipment used, I think that it's typically quite a bit less, what's the right word? You know, you don't need this huge mega deep UV thing that's flown in on a 747 and costs $1 billion to do this, like you do for logic and processors. So, you know, the fabs themselves are huge. Most of this is made in Asia, but in terms of the equipment, it's, you know, nothing terribly huge. I mean, not like the big deep EUV etchers or photolithography. I mean,
So the feature sizes are typically much bigger, I guess, than the fine line semiconductor. Are the fabs usually dedicated to memory, so it's not a mixed, you know, it's a dedicated fab?
Yeah, they are. And you know, the companies that make memory are companies like, you know, Samsung and Kioxia. And, you know, whereas the ones that do logic devices are Intel, TSMC. It's really a fairly different, a different group of companies that make memory versus logic and processors.
Thank you.
Hey, John, how long does it take to make one of these? You know, get a complete memory device. Is it all in one fab?
Yeah, it's all in one fab. I don't know how long the whole process takes. I don't know, maybe Katie knows. She can chime in if she knows the answer to this.
I'm afraid it does vary fab by fab, so there's no one stock answer, I'm afraid.
Yeah.
I don't know if is it days or is it months, you know?
It's probably on the order of days. I don't think it takes months to do this. You know, the mold stack itself is, you know, on the order of, I don't know, minutes to hours, somewhere in that. That's a pretty wide range. But, you know, depending on how many layers you do, it's, you know, doesn't take all that long to do that.
You know, also for the less technical people, where would you see these things?
Well, I mean, look at your phone, right? The phone I got just a few weeks ago, or months ago, I guess, you know, has something like 64 gigabytes of storage. The one that it replaced had about 4, right? And it was 5 years old, right? So all of that is flash memory. That little thumb drive I showed in my first slide was flash memory. My laptop right now, pretty much any laptop I think you buy, it would come with a solid state hard drive standard, just because it's low power, more robust, faster. So those are really the applications that it's used in. But I think that, as Greg noted and some other people know, it's moving into other applications like, data centers and things like that.
Hey, John, this is Randy. How big is a cell?
Each individual cell, I do not know off the top of my head. Okay. I apologize.
That's okay.
It's probably like a medium-sized transistor. You're a double E. You should know how big that is.
Well, I was just looking at, like at the microprocessor industry, they're at 5 microns, 10 microns, 15 microns. I sort of wonder if you have a metric like that.
Again, really kind of the key is that we're not really getting, the big focus is getting taller and taller, not getting smaller and smaller.
Are you could you get smaller?
We could, but just with, I think the supply chain, which includes companies like Lam that support these, are really more focused on being able to deposit better, deposit faster, more accurately, or etch better, sharper features. So, there isn't that much of an emphasis on better photolithography or something like that to make smaller features.
Okay, thank you. Great presentation, by the way. Thanks, John.
Thank you.
Say, this is Ed Friedman. I have a question about what is known about the photosensitivity of the cells. The reason I bring this up is that Miller and I are in the photonics world. And in the early days of memory, people made cameras out of memory devices by shaving the epoxy off the top. And you had a nice, so I'm not talking about 3D now, I'm going back to this process in a 2D geometry. What do we know about photosensitivity?
Well, there's a lot of silicon in this, and as you know, silicon is very photosensitive. So. Yeah.
Are there any other questions? Okay, well, I'm just going to give a round of applause here for John. That was really thanks for putting in the time. I certainly learned a lot today, and
thanks, John.
Appreciate it.
I enjoyed doing it.
I did have this recorded. I don't know exactly what I do with that, but I'll figure that out and let people know, the people that weren't able to attend. I know I got a couple of emails from people who said that they couldn't make it, but they hoped I was going to be able to store it, including Carlos Quintana. And so in the future, we invite others to do presentations. I think I may do a reprisal of my Panama Canal, how most big engineering projects are like the Panama Canal project. And I'm thinking about in the future possibly doing one on, believe it or not, glaciers, which will be interesting.
Yeah.
And Kirk is thinking about doing one on foundations for skyscrapers. So if you have anything that you're interested in, it could be nature, it could be birds, could be sound. I know we have at least one sound engineer here that might have something interesting to present.
Veterinary medicine.
So again, thank you for attending this meeting. It's science for the bored. I hope you're less bored now than you were when we started. Thank you.
Thanks, guys. I'm glad I joined.
Thanks so much. That was great.
Good night.
Bye-bye.
Bye-bye.